Okay, I have 7:30. Unfortunately, this screen won't turn on, so I'm not using the camera. So if you're watching the lecture recording later, there won't be a camera. But we are still recording the screen. Right. So we're going to continue this chapter. We're still on this piece of the case study of MIPS, and we're still going over this set of possible instructions. Today, we're going to be focused on data movement instructions. So that's load word and store word. So here's our load word. So it's going to write to the register RT the memory data at the memory location with the base address of the data in register RS plus some sign extended immediate. So we first need to calculate this address with the register field plus the immediates, and then get the data from the memory at this address to store it into register RT. And following the same format as R-type instructions, the first register is always your destination register. So although RS is the first register in the field of the instruction, in the assembly code, first register is your destination register. So this is RS, which is your base address. This number is your immediate. So RS plus this immediate gives you the memory address, and we need to put that data into T1, which is RT. And then we have this similar thing with store word, except now our destination is this memory because we're moving from register to memory. So in this case, RT is not a destination because there is no destination register. It's just the data that we are going to store into the memory. And we have the same base address plus some offsets with the sign extended immediates as our memory location. So here we see the same thing. It's just the opposite. We're storing from T1 into this memory. Okay. So here's our example. We have PC is pointing to address 4 in memory. So we're going to first read that word from our memory and store it into the instruction register. Then from the instruction register, we have some data path logic that will decode this instruction and tell us that we need to read from register R1, the base address, calculate the full address, which is R1 plus 0 in this case, and then get that memory location out of main memory and put it into register R2. So here is our R1, right? It's 14 in hex, which is 20 in decimal, right? So we do 20 plus 0 because we have 0 as our immediate, and we get 20. And then we take that memory address, fetch from memory at location 20, and put it into R2. So now R2 is containing the information stored at memory location 20. And then we increment PC, and we increment by 4 so that we are word aligned. And now we're going to grab the next instruction, which is the store word. into the instruction register. So store word, it's just the opposite of load word, right? So now I want to take the contents of register R2, which is what we just loaded from memory, and store it into memory location with the base address of R31. So we do our address calculation, R31, and we add 0 to it because our immediate here is 0. Get 18 back, which is just 24. And then we're going to take the contents of register R2 and store it into that memory location. So with these two instructions, we basically just moved the data from memory location 20 to memory location 24, or not really moved, but copied, because the other one still exists. So we see how load word store word works. No questions on this? Okay. So here's another example with a line of C code, and we're going to translate this into MIPS. So we're going to assume that A and B are in S1, S2, and the base address of the array A is in S3. So really what we need to do here is first copy the data of A at the 8th element into some register. We're going to put it into some register T0. And then once it's in register T0, we can add T0 to S2 and then store it into S1, right? So here's our load word. We want to store into T0. We have the base address S3. And because each one of these is going to be one word, right? So we do 8 times 4 gets us 32. So now we're pointing to the 8th element in the array A once we do this addition, and we're going to store that information into T0. And then S2 plus T0 is now B plus A, S1 is A. So is there any question about how to translate like very short high-level C code into MIPS assembly code? We can all do this? Yes.
The 4, because it's 4 bytes per word, right?
Yes.
Okay.
So I'll give you this on exam. Everyone gets this. Yes.
When you do the load word,
Mhm.
is there a limit to how much you can increment in the array?
Yes. So we'll go over the format of this instruction, but basically this field is a 16-bit field. But one thing that is neat about it is we know the last 2 bits for a memory location to be word aligned is always 0, 0. So we actually don't use the last 2 bits. So essentially we get 18 bits with 16 bits because we just put the 16-bit number here, and then it gets left shifted by 2 by the hardware. So we don't have to specify those 2 bits. So it's not shown here, but that is what will happen. And it's shown this way because it's just simplified here. But we'll show you later on when we get to the single cycle implementation, how that works. All right. So now we want to translate the same code, but now rather than a fixed address, bless you, we have another variable. Okay. So we have A, B, and now I is in S4. Base address of A is still in S3. So we need to compute the address of the element in the array at the location I. So our MIPS code is going to look a little bit different. We have a little more instructions that we need to do here. So the first thing that we're going to do is we're going to add into T1 S4 to itself. So that basically multiplies I by 2. And then we can again add T1 to itself, which is just now 2I. So now it's 2I plus 2I is 4I. So that basically gives us S4 multiplied by 4, which is just I times 4. Another way that you can do this is just shift left logical S4 by 2 into T1, and you would do the same thing but in one instruction. Next, we're going to take T1, which is 4I, add it to S3, which is the base address of A, and put it back into T1. This is now the address of the array at the current element I, right? Because we calculated the offsets here by multiplying I by 4, and now we added the offsets to S3. And now when we do our load word, we don't have this offset. And the reason that we have this instruction, rather than just putting T1 here and S3 here, is because this is an immediate field. You cannot put another register here. There's only 2 registers to specify, the destination and the base address. So that's why we needed to do this instruction here. We can't save an instruction by putting our result of T1 from here into here with S3 here. Do we see this? It's just a common mistake that happens. And then once we have the data in T0, it's again very simple. S2, which is B, plus T0, which is A at I, into S1. Right? So this is asking, is there another way to compute the address of A of I? And that's what I was talking about with, you can, rather than 2 instructions doing this, shift left logical by 2. Gives you multiply by 4. All right. So we have instruction sequence operations. We can do conditional branching. So if a condition is true, which it would be branch equal, or well, I guess that it's both if they're true, but if 2 registers are equal, we can do branch equal, or if 2 registers are not equal, we can do branch not equal. And you can also do unconditional jumps to target address with jump register, which is jumping to the memory address stored in a register, and then jump and link, which is similar to jump register, but it has an extra step to it. And we'll talk about those extra steps when we talk about procedures. And more conditional set operations. So set on less than, we talked about this a little bit already, and set on less than immediate. All right, conditional branching. So this is going to be used for if statements, for loops, anytime where you need to move back up in your code. So branch equal, and RS is one of your operands, RT is your other operand, and basically you're just going to be doing this, which is if RS and RT are equal, then we're going to increase PC not just by 4, which is your normal increment to go to the next instruction, but also by the offsets specified to reach this label L1 in the code. So L1 is going to be another label somewhere else in the code, and this can be up or down because this branch address is a sign extended immediate. And then branch not equal is the exact same instruction, except now we're going to branch if the registers are just not equal rather than equal. So here's our example. Branch not equal, S3, S4, go to L1. So basically if S3 and S4 are not the same register, like not the same contents in the register file, then we're going to jump to the L1 label in our code rather than going to the next instruction. All right, unconditional jumps. So jump to L1, we're not even going to check a condition. We're just going to jump our PC address to this label L1. And then jump register is we have this register RS. Put the contents of register RS as the address of PC. No condition. All right. So now with conditional operations, we can do some more complex compiling of C code, right? Because now we can do if statements. So here's our MIPS code. So our first thing that we're going to do is branch if S3 and S4 are not equal. So S3 and S4 are A and B, right? And if they are not equal, we're going to go to L1. But if they are equal, what we should do is X equals Y plus Z, right? So right under the branch, which is PC plus 4, which is what happens if the condition is not true, we're going to do this X equals Y plus Z. So X is S0, Y and Z are S1 and S2. And then after that, we have our L1 label, which is going to be our sub, which is X minus A. So destination is X, and then first operand is X, and it's a sub operation. So second operand is what you're subtracting from the first operand, which is A. And this is not a complete code. There would actually be another instruction here that would be another branch to skip this, because as this is right now, basically, if this is not true, you would do this, and then this is right after, so you would do this too, but there would be more code here. All right, so we can also do if else, right? So again, same mappings, X, Y, Z, A, B. So branch not equal. So if A and B are not equal, we're going to do the else. So this is our this is the case where they're equal, right? Because if they are equal, then we do PC plus 4. So X is Y plus Z. And then here is some additional code that could have gone in the other one, right? Right after we do that, we just exit this program. The other piece is now, if they are not equal, we need to do this subtraction. And then after the subtraction, we're going to exit. So any questions about if-else statements? How to convert them? Okay. What about going the other way around? You're given this, can you write this? Yeah, you'll be given this, and then you're given this. Okay. So we can also do looping now, right? So now we want to do this. So we're going to do some operations, and then at the end, we're going to check if I has reached the end of the array or the end of where we want to do our operations on the array. And if that is true, then we are going to just continue. But if it's not true that we haven't reached the end, we're going to go back up to do the loop, but with an incremented I. So here is our loop. So like we talked about before, shift left logical, right? That's going to, and we're shifting left by 2, so it's going to multiply I by 4, and we're going to put that into T1. So what's the next thing that we're probably going to be doing? We first need to add before we load. Right? So we're going to add our offset to our base address, which is S5. And then what do we do? Load word. So opposite. Yeah. So load word to get the memory, the data out of memory into the register file. So we're loading A1 and we're putting that into T0. And then now we're going to add 2G, and we're going to add the data from memory, which is in T0. And then next thing we're going to do is increment I. And now that we've done all of the computes before our check, next thing to do is branch not equal. So we're going to check, is I not equal to H? If that is the case, we're going to go back and continue until I is equal to H. So this is simple enough too. This is, again, mostly review, right? Okay. So now we're going to be able to see the examples where we're going to use this set on less than. So this is useful when you want to do something like branch if a register is less than a register, or if you want to check if something is less than intermediate. The set on less than will set the destination register to 1 if RS is less than RT, or if RS is less than an immediate value. So what you can do is check your condition with set on less than, and if it is true, then the register T1 will be set to 1. And then depending on what condition you really wanted, less than or greater than or equal to, you can branch not equal or branch equal of the destination register from set on less than with register 0. Because now if T1 is 1, that means that this was true, right? So we're going to do this comparison. And then if T1 is 0, that means that this was false. Okay. and then T1 would be equal to 0. So that would mean that it's greater than or equal. Right. So one thing that you might be asking is, what about on less than or greater than or equal? Well, the reasons for these not having their specific instructions is you can kind of convert any code that's doing that to be doing the less than. So your compiler will just do that for you. And these comparisons are much slower than equals to or not equals to. So that means that we can optimize for equal and not equal in terms of our branching instructions. And with the help of set on less than, we can do those other inequalities. So it's just a design compromise in order to be more efficient on the hardware side. All right, so this is your first instruction, not instruction, first question. And I need to actually create the poll. So think about this, and I'll tell you the code when I have it. Okay, it is active now. Your code is 391. Yeah, I don't think many people are still thinking about this. We are not quite at the threshold. There's one very popular answer that is the right answer, but there is still one answer that is somewhat popular that is not quite the right answer. So do talk to the people around you Let's see if we can move everyone to this more popular right answer.
So when you change it out. Since it's more, I thought it's for small ones. It was true, then he goes to the next stage. That's yeah, I think.
Okay, do change your answer if you were convinced to change. I see some people have changed their answer. Okay. So we still have two popular answers, but we did have some movement towards the right answer. So does anyone want to tell me what they answered and walk through the code as to why they answered this? Yeah.
I chose A.
Okay.
I forgot what SLT stands for, but
Set less than.
set less than. So T0 is supposed to be the first operand, so I think that's I. And J is supposed to be T1, and then it's not equal to. So the other one was equal to, so I mean D. So that's why I just kind of like eliminated B and C because of that, and because of the second line, I eliminated D.
Okay, so first step was set less than sets T2 to be 1 if this is true, right?
Mhm.
So assuming this is true, T2 would become 1, right? And now 1 is not equal to 0. So we would go to false, which is actually going to skip this. So what we needed is the opposite, right? So we just need the opposite of not equal. So that's D down here. Everything else is the same. We just need the opposite condition.
Second line kind
Yeah, it's a little bit confusing, but once you look at it many more times, and sometimes it also is helpful to just walk through it one line at a time so that you can kind of make sure, oh, this is what I was expecting, or oh wait, that's not what I was expecting. But do you see it? Make sense? Okay.
I just didn't know that the register T2 would become 1 if it's true.
Yeah, so it's just that will also be on your MIPS sheet. So it's not something that you would memorize. You would have to memorize, but it could be helpful to memorize that so that you don't have to look through the MIPS sheet during the exam. Okay. But those were the two popular answers, and I see many people have changed to D, but A was like 30%, D was 60%. So do not feel bad if you chose A. It is a very common mistake. All right, so instruction formats. So our instructions are encoded in binary, right? That's the machine code. So we need to figure out what this 32 bits binary code really means in terms of our instructions. And there are a few things with instructions that we should cover, like There could be variable width instructions where it's not fixed 32 bits. And this can be used for applications where code size is very important. This is not really a problem nowadays because storage is very cheap, right? So code size is almost never a problem, even on things like our phones. So most ISAs, especially nowadays, are going to go with fixed width because we don't care about storage limitations, because it is better performance, because we have a more uniform instruction decoding. And if we have a more uniform instruction decoding, this on the fly, not decompression, but I would call it decoding of the instruction to figure out what it means, is able to be better optimized on the CPU. So for MIPS, we have this fixed instruction width, and we've seen this already, but we have these 3 instruction types. We have R-types, and the opcode will tell us what type we are. And for some instructions like the I-type, it'll also tell us what the instruction is. But for R-type, the funct code tells us what the instruction is. And then we have more uniformity, like between the R and I type. We have RS and RT also in the same field, like the same place. And then we have RD because we need a 3rd register for R types. Shamped is the shift amount for shifting. And again, funct code is to tell us what the function is. And then rather than those 3 fields, we have this 16 bits constant or address. And the reason it's called constant or address is because this is your add I or I for your constants set on less than immediate. That's also this type. And then the address is because I type is for load word, store word. And I type is also for branch equal, branch not equal. So that's again going to be an address. But essentially they are all just this 16 bits sign extended immediate number. All right, and then we have J types. This is for our unconditional branching. The jump and link, jump register. Well, actually not jump register, but these unconditional instructions that need a much longer address. So this is again following our 4th principle. We have these uniform formats so that we don't have complicated decoding. And it's going to give us larger instructions for the most part, because now we have this fixed 32 bits with instruction length, where we could have shorter instructions. But again, it's a good compromise to make because storage is cheap. But performance is not easy to come by. So R-type instructions. So opcode for all of our instruction types are 6 bits. It's in the same place for every single instruction. It's in the first 6 bits of the instruction. And then we have RS, which is the first source, RT, second source, RD, the destination. So just as I mentioned before, on the instruction format, RS comes first, but on the assembly code, destination comes first. So RD is our destination. So it can get a bit confusing when you're doing this at first. But again, you don't have to memorize this. You'll see on the MIPS sheet for the instructions, like the description of it says RD is equal to RS plus RT if you're doing add. So from that, you can figure out this formatting as well. And this format is also on your MIPS sheet. So you, again, don't have to memorize this either. But it is good to get familiar with it so you can be faster at it. And again, shift amount is the amount to shift by. But if it's not a shift instruction, usually this is just all zeros because it's not used. And then funct code is it an add? Is it a subtract? Things like that. So here is our example. So we want to perform add, and we're going to store the results into T0. We're adding S1 and S2. So we're just putting, for now, it's just whatever the opcode is for R-type. We don't know what it is yet. It's on your MIPS sheet though. Okay. But we do know that the first operand is S1, so it needs to go into RS. Second operand is S2, it needs to go into RT. And then destination is T0, so it goes into RD. And we are an add instruction, so we need the funct code for add. And because we're add, we're not a shift, so shift amount is 0. Right? So then if we go to the MIPS sheet, we can look up for add, which is not add I. Opcode is 0. And then we'll also see that the funct code for it, because it's an R type, it has opcode and funct code, is 32. And then we'll also look at the MIPS sheet, look up what S1, what the real register number is, 17, and S2 is 18. It's not always the case that it's just going to be incremented by 1, like S1 and S2 here. It's just incremented by 1. The temporary registers are split across. So there's like 8 clumped together and then 4 clumped together somewhere else. So don't always trust that it's going to, I just looked up S1, so S2 must be S1 plus 1. So just do double check that. And then T0 is register 8. So now that we have all of our fields in decimal, we can convert them to binary. And now we have our 32 bits instruction. And once we have it in binary, if we want to look at it in a more compact form, we can convert it to hex. And one thing to keep in mind when you convert this to hex, this is 6 bits. Oftentimes, students will just convert the 6 bits into 2 hex, or 2 hex digits here, but that's not correct. You need to grab the first 4, and then across these fields, the next 4. So do be careful with that. Same thing sometimes happens going from decimal to this binary field. Okay, so that's probably one of the most common mistakes I see with once you have all of these, converting them down here. So your last thing for today is this last poll question. So do this on your own. And if you need it, the MIPS sheet is on Canvas under the Files tab. Is anyone still thinking about this? All right, so we are past the threshold for this. And we can look at this together. So first thing that we should almost always do is opcode is 0 and func code is 32. I'm going to look at my MIPS reference sheet. Do remember the MIPS reference sheet is in hex. So 0 is same as 0, right? But 20 is 2 times 16, which is 32. Okay, so this is 32. So 0, 32, we're at. So we know it's an add. And the next thing is RS is register 24, RT is 0, RD is 24. So we know that RS and RT are the same. And we know we're an add. So far, this one is pretty promising. This is RD, this is RS, right? And then RT is 0. And we know that $0 is 0. And that matches. So now we just need to check is T8 24. So again, going to the MIPS reference sheet, the registers are just down here. So T0 through 7 are 8 through 15. So like I mentioned, they're not all grouped together. T8 actually starts at 24. So we've just confirmed that we like A, it's add, RD is T8, RS is T8, RT is 0. Okay, so last thing is you do have a reading for Wednesday. It's the continuation of chapter 3.